after the hour. Let's get started. Welcome everyone to the Theoretical and Computational Biophysics seminar this week. It's my pleasure to host Professor Miguel Machuqueiro from University of Lisboa. By way of introduction, Miguel received his initial degree in actually biochemistry from University of Lisboa, but then he moved on to go to Switzerland, University of Bern, where he did his PhD in bioorganic chemistry, still doing actually organic synthesis, not doing computational work. But then again, he did a postdoc back in University of Lisboa with the famous Antonio Baptista's group in the theoretical biology and chemistry group, during which he worked actually concentrated on the effect of pH, which we know it's a very important aspect of our simulations that we usually look away from and say, okay, everything should be fine. But as we know, the pH changes a lot during the simulation, and it would be very nice to have a method that can efficiently change the pH or change the protonation state of the classical systems that we simulate, and we would like to understand. So, so in 2009, so he joins the faculty of Department of Chemistry and Biochemistry at University of Lisbon, and he has been since then working on what I said, the effect of pH on macromolecular systems in biological systems, especially in membranes. The way peptides interact with membranes depends on the pH, of course, and the way many of you have been working actually on proteins that interact with the membrane. When they get close to anionic lipids, what's going to happen to the pH of those groups? So he was kind enough to accept our invitation and join us at very late time, 9 p.m. in Lisbon. Thanks again, and he's going to talk about increasing the realism of MD simulations by adding pH effects. Again, thank you again, Miguel, for joining us tonight or this evening, and we look forward to your seminar.
Thank you very much for this really nice introduction. So I'm going to share my screen now. I think it should go okay. It's always dangerous when I share my Windows virtual machine.
Okay, it works fine. Perfect.
Yeah, so if I still can see, yeah, I can see it now. So I think you can see it?
Yes.
Okay, perfect. So this is my one of those presentations I really like, because I know that most of you are interested in the subject. If you are not too much into these pH effects on biomolecules, at least you work with biomolecules, and I don't need to explain most of the stuff that I do. And the presentation is not really like a very hardcore presentation. I'm a very practical person. If you really have questions regarding the method, you can ask them in the end, no problem. And I'm just going to take the opportunity to showcase a little bit of what we can do, because I think we can do stuff that is slightly different from the literature, from what you can see from other people's methods. And some of you probably know some of these methods that I'm talking about. Well, a very brief introduction is, at the beginning, we have molecular dynamics. That's the base, right? We start from molecular dynamics. We have a big mess of confusion. We have a lot of sampling, can sample molecules. But actually, there was the benzene going there, of course. And we can sample the conformation of small molecules, peptides, and of course, even proteins. We can sample all of them. And the moment we sample the conformation, we are applying a model. We are applying a force field with all these merits and all its caveats, right? So there will be problems that we have to know, and there will be questions that we might want to ask, but probably we shouldn't because of sampling limitations, time scale limitations, all of these kind of stuff that we are used to have in our the way we talk and discuss our methods, right? And of course, most of the time, what we are interested in is like big conformational transitions, and this big conformational transition requires enhanced sampling and all of these kind of methods that probably you also know a little bit about. because I'm a computational biophysicist, there will be membranes, right? We always have, at least my interest started from very early into the membrane, understand how it blocks water, the way it separates, how the adhesion gives the strength of the lipids, the phase transitions, all of these. And I was also very interested in the beginning from the pH effects and how to introduce these pH effects first in peptides and proteins, and later on even in lipids, because lipids are also subject to protonation, just like any other biomolecule. When this is my first slide that I usually put here, kind of a provocation. So this is what most people do on the left side. So this is constant protonation, and constant protonation is any let's say MD package does constant protonation. Nowadays, there's a couple of them that already do constant PHMD, which is cool. This is on the right side. But most people just run constant protonation, fixed protonation simulations. And this is what we use. I very rarely we use regular MD in my group, to be honest. Only when it's like unnecessary. And sometimes it is unnecessary to run constant pH. But most of the times it isn't. And even if you suspect that, okay, pH might not have an effect, if we are not completely sure, we run constant pH. And of course, when you prepare your MD protocol and your MD simulations, you have to choose the correct protonation states. And here comes the real problem, because if you make a wrong assumption at the beginning, you most likely have like a huge error. The electrostatic potential comes wrong. Your ensemble, conformation ensemble, comes a little bit skewed into some direction. The problem is you don't even know that happened. So you are just sampling stuff that probably it's non-physical. And of course, if how can we prepare this protocol, and how can we select the best protonation states? Usually you can start, and we all start our simulations from two different setups. Very often we start from X-ray structure, but nowadays, because there's a source of structures coming out from computational world that is so large that the temptation to run these calculations on ND simulations, structures coming from ND simulation, homology modeling, or even AlphaFold, it becomes increasingly large. So now we are not only limited to the PDB data bank, we can start our simulations for anything. The problem is that the first step that people usually do is actually do a pKa calculation on this. And the thing is, pKa calculation on a crystal structure or an NMR structure, which is actually an NMR solution, because they are kind of average out for different reasons, but they are kind of average out. They tend to work rather well. It's not perfect, far from that, but they tend to work. But on the other hand, if you start and you just try to predict a pKa out of a MD structure, then you are really completely wrong, because you are no longer have a good prediction of the macroscopic pKa, because those structures will be biased, because carboxylic acid will, in those simulations, in the energy minimization step that you might have after your homology modeling or AlphaFold, if you do something like that, a computational step, you already took a decision. You already decided to add the proton or remove the proton. And by taking that decision, you bias the system towards one of those fixed states. And that is why the system is biased. And how can we do this? There are a bunch. I just put here a few of the classics, some of those platforms that we all know about. So H++ is quite a nice software from Virginia Tech. Delphi pKa is a really nice one from Emil Alexov. It's a good friend. And I always advertise his website because he was the first to do this with one of the first to do this with Delphi, to have this website and a nice database of experimental pKa values also. ProPKa, which is by far the worst. It's the simplest. It's it's the beginning of almost machine learning, kind of, but it's a glorified QSAR experiment. If the developers were here, they would just crucify me. But in all our benchmarks, this was the one that always behaves the worst. But this somehow is the one that people use the most. I don't know.
Sorry, Miguel.
Yeah, go ahead, Ivan.
In fact, that was one of my questions that I wrote down to ask you. Which one is the best? Or which one?
I would say the best is mine, but I'm a bit biased.
Of course.
In fact, it depends on the question. But if you want a little bit of detail, if you want complex systems, they are all wrong. I'm sorry, because they are all biased towards the structure. Even if it's an average structure, they will give you a good guess for a soluble protein. But most of the interesting systems that we want to study, they are just not good enough.
I see.
But to predict, this is the PyPK server that this is developed in my group, and this runs Delphi and Poisson Boltzmann solver, and then Monte Carlo to get the PKAs. It's very fast, and we have this PK-PDB database, which means that if you just stick PDB code there, it will not run the calculation because we pre-ran the whole PDB data bank, so it will give you automatically the PKAs. So it will be faster than ProPKA. You have no reason to use it. ProPKA, you can use the one developed by the Portuguese, which is always a good advertisement for my group. And this is the interface, and it's quite easy to use. I think if you test it, you'll like it. But this is the reason why I came here. Constant pH molecular dynamics. Our method is probably one of the simplest methods to explain. Of course, if I don't go into the details of Poisson Boltzmann, which is sometimes tricky to explain, but if I try to explain it in boxes, it's very simple. So imagine a method where you run molecular dynamics, and at a certain interval you stop, and then you just go into Poisson Boltzmann and you ask, okay, for this conformation, does this titrable site likes to have a proton or not? And then it gives me back an energy and an energy difference. And I run those energies with Monte Carlo, and Monte Carlo will sample. And instead of giving me the most probable, just give me the last protonation state that it arrives, like after 100,000 or 1,000,000 steps of Monte Carlo, give me one protonation state that you ended up, because that will be representative. I pick up those protonation states, I rearrange my topology in the MD, and then I continue to run for a few picoseconds more. So it's very simple to explain. Of course, there's the trick of the relaxation, because we change the protonation state, the water is not rearranged, so we have to fix the protein and let the water relax. So we studied a little bit to see how much time does it take for local water to relax. We give it like 200 femtoseconds. You don't need more, and it's enough. The water rearranges, and then it continues quite happy with the simulation. So it's quite simple. If you have more questions, I can give you. And with all of this, in the last maybe 15 years, I've been studying the titration of proteins. That is the easier part. It's quite simple to do titration. It takes some time because you have to run one simulation with replicates and all the sampling per pH value. And afterwards you make PKAs, right? And but then if you think about it, you start thinking about, okay, but I can study very complex stuff. So here I have donepezil, which is a tertiary amine, so it can change protonation state. And I can follow the pKa of this donepezil while it goes in or getting out of the pocket of acetylcholinesterase. So I have an inhibitor, it's a non-inhibitor, it's a drug for Alzheimer's, and I can follow the protonation. And the cool stuff is, if you see the protonation at physiological pH, what is the protonation of the drug? Of course, if it's in the outside, it will be very high because it's a Lewis base, the pKa is like 8.5. So, but the moment it goes into the pocket, you see it feels the interactions with all the side chains. And when it reaches the X-ray structure, which is somewhere around here, the protonation is 0.5. So now you try to do some docking with this. It's a funny one, right? So should I put the proton, not put the proton? Yeah, you should do both, and then in the end just present data for both, and say, well, I don't know which protonation state will be more relevant. Probably one of them, or one of it will be more stable. This 0.5 might be 0.2 or 0.8. Of course, there's an error related to this calculation, but it's a good thing that helps us think about the problem, right? So this is a nice example that I show. And now things become more complicated. So what if I have a membrane and my lipid, it's like oleic acid, has a pKa of what, like 4.75 or something like that? Let's think about 5. So if I have this, will all of my oleic acids be ionized? Of course not, because the charge repulsion is so high, the pKa, the first few you can protonate easily, but the ones that come after becomes much more harder to protonate. And then there's experimental data on this, a lot of things. So what we did is we just ran constant pH molecular dynamics, and we start from the bilayer. We know that the bilayer should be stable somewhere around here in this region. Over here, it's already too ordered. When you acidify too much, it becomes an oil in experiments. We know all of that. And then after some time, in our case, it's where you stop having dots with colored dots. When you don't have colored dots, it means that the system exploded. And what the experimental sees the dispersion. So it just sees that because limpid, the moment it gets a dispersion. So we could model the whole transition, which was really cool to do. We did this almost 10 years ago. And as you see, the level of complexity is increasing. So now we are interested in a peptide that doesn't have has no structure let's say at neutral pH, because it has a lot of charge. So it does not have a structure. But the moment it slightly acidifies the medium, it folds, and then it folds and inserts into the membrane. And this is the flip peptide. Some of you might have seen something about this. This was developed in Don Engelman's lab in Yale, and now it's continued to be studied, and it is continued to be developed by Reshesniak and Andreev in Rhode Island. And in a collaboration with them, what we wanted to do is, what is the trigger? Because experimentally, we know there's kind of a trigger of insertion, I'm sorry, at with the pKa of 6. And what we wanted to know is, what is the residue or the residues responsible for this? And what we found out is, after simulating the peptide inside the membrane and following the pKa along the membrane insertion, we found out that the residue needs to be one specific. It's like aspartate 14, and we could identify and say the pKa is around 6, which really identify it as a trigger. And of course, if you can do all these simulations with membranes, we can. Can I just have a couple of minutes just to go and grab a little bit of water, because I forgot to bring water here.
Absolutely.
Yeah, just give me. It will be 20 seconds.
Sure. We have to start using this, guys. Pro pKa is the worst currently. Well, I mean, this is not in NAMD. This is apparently in Chromax, but at least the pi pKa might be something interesting to try.
So how often do you have a seminarist die on you on thirst? That's common, right?
Sure.
So I was on the membrane permeability, and the reason why I brought up the idea of membrane permeability is because I have an example for you, and this example is related with the membrane permeability of drugs, and they are anti-tumor drugs. And to understand let's call it how important this subject is, we have to think about some of these drugs that we take. Tumors tend to create a kind of an environment to provoke a kind of resistance. It's called multi-drug resistance. And this multi-drug resistance has different mechanisms. And one of them, not very well studied in terms of acidification, is this tumor microenvironment. It's known that it's acidified, and it's that acidification leads to a lot of triggers, a lot of stuff that can make the tumor cells expel and keep the drugs away, and also to entrap these drugs into lysosomes, because lysosomes become very acidic and they also can trap the drugs there, taking them from the cytoplasm where they can actually do their bidding. So this tumor acidity is a big thing, and it's probably now a major issue in my group, where we try to understand how does this acidity impact drugs. We're also interested in what this acidity can impact many biomolecules, but in this example, I'm going to concentrate on drugs permeability. So it's what happens to these drugs when they interact with membranes and how they cross into cells. That's why all these methods to calculate membrane permeability are very relevant. But to simplify this and to give you kind of a picture of what is going on. So in a normal cell, these are the pH values that they're more or less common. Of course, they will change a little bit if you change the type of cells, but typically you have like 7.2, 7.4 in plasma, and lysosomes, they are acidic. And then when when cells become tumors, or cancerous, what happens is there is a slight, not all authors will agree with this, but there's a small increase in pH on the inside, because they efflux all the protons that are being formed, and they efflux it very reliably to the outside. The outside, because the tumor, when they becomes large, perfusion is not good, protons get trapped on the outside of the cells, and then it acidifies. And there's also the issue of lysosomes, which become slightly more acidic, and even tumor cells also produce more lysosomes. That's also important. Oh. But what happens to these drugs? I've been claiming that anti-tumor drugs, they can have a problem with this. The reason is because of this. So I give you 4 examples of 4 anti-tumor drugs, and I'm going to call your attention to the fact that they are Lewis bases. So they have pKa's between 7.5 and maybe 9.5. So like weak bases. And I picked them up just because they are compounds that are, you see the names, they are being, maybe the names are different in Portugal and in the US, but they are being given in hospitals nowadays. They are still given. I think they're all still being used. And they are used for different kind of cancers. There was no reason. And I call your attention to the fact that they all have this group. And the reason why this group exists is because being a Lewis base at physiological pH, this big, bulky, hydrophobic compound will become charged. And by becoming charged, they will be more soluble, water soluble, and you can take it as an injectable or a pill or whatever, right? So you don't need to create like a big drug delivery system for these compounds. Mm-hmm. And how does that happen? So technically, the compound at pH 7, because the pKa is 8.5, it will have this possibility to remove, to kind of get rid of the proton, and this in water will happen at pH 8.5. And if you are at pH 7 point something, so this means that 90-something% will be protonated. And the thing is, when this compound interacts with the membrane, we know that there is no specific transporter for them. Most of these compounds, they just cross membrane. They are so hydrophobic, they don't have any problems. They will accumulate at the water membrane interface, and then they will just jump to the other side. But to jump to the other side, they need to go through this deprotonation. It's called transient deprotonation. So they lose the proton, they get to the other side, and then they will reprotonate again on the other side, and then they continue their merry way. Although the partition to the membrane will be very high, so 99% of the compound will be interacting with some sort of membrane or something else that is hydrophobic. That is, these compounds, they don't like to go to water, as we can imagine. But when we started studying these compounds, we used molecular dynamics. In fact, we use constant pH molecular dynamics, but it's still not molecular dynamics. We have a limited sampling. So what the best thing that we do is we study the interaction of the drug into the water membrane interface. Well, it will interact with the phosphate region and then interact with the lipid tails until a certain moment. And then it just doesn't go deeper than that. We don't see crossing during MD simulations. You need to have much smaller compounds to see it go through the membrane.
I see.
And because we did these simulations, so we have all of this sampling, it was interesting just to study the protonation. So what happened to the protonation when the compound, you saw the protonation of the drug go inside the protein, but something similar could happen to the drug go inside the membrane. And this is what we observed, which is cool. So at pH 8.5, you know that in water, because the pKa is around 8.5, so it should be around 0.5. So first point we have is here, because we use very small boxes. We don't have so much something on the outside. But I suppose that if you continue to go away from the membrane, you see the gray area is the membrane, lipid tails. Around here at the interface should be the phosphate and the choline groups from the phosphatidyl choline. And then here should be water phase. But you see, the moment it starts to interact with the phosphate, the first thing that you can see is it likes to get a charge, protonated. And the reason is phosphates are negative. Cholines can easily move to the side so that the compound comes in. The phosphates can also move a bit to the side, but they cannot move as well as the choline group. So the phosphates, they kind of have to stay there because they have two anchors attached. And this makes it that the compound feels the negative from the membrane, and then it inserts. And then comes dissolution, which is, well, it's expected, right? So we have this compound. The moment you start to force, or not force, but the moment you start to see the compound going inside, dissolution will happen, and all of these points tells us the average protonation. And then when it's like 4 angstrom below the average phosphate position, then you have neutral compound. So it easily deprotonates at pH 8.5. And you can see this is just the abundance. This is where the compound likes to be, because these compounds, they just love to stay on the part just below the phosphate. And at pH 7.5, which is more close to the physiological pH, then you see that the profile is quite similar. It's as expected, I think. If you just think about of the protonation, the forces involved should be similar. And the abundance is very cool, because now at this pH, it's jumping between the outside and the inside, so the above and below the phosphate region. And then if you continue to go to more acidic regions, you see it's more difficult to do this transient deprotonation, and the compound just doesn't go inside the membrane as easier. And of course, if you go really more acidic, like 5.5, then we have a problem. We do have deprotonation, but it happened not very often. It was very difficult to do this. And if we use all of this information to calculate pKa's, then we can kind of think what is going on. So pKa in water should be this. It is hollow sphere here. But the moment you start having sampling, we see the pKa is very similar to the one in water. But then when it starts to feel the interaction with all these lipids, and after dissolution, you can see the pKa comes down. this is the shift in the pKa. So the proton binding affinity becomes smaller and smaller. This is what allows the compound to lose the proton, because suddenly it's in an environment that it doesn't like to have a proton anymore, and then it goes. And of course, this happens for all of these Lewis bases. This is a mechanism that allows compounds to go inside the cells and do their bidding. Where is the problem? Problem is that the strength that you do, which is how deep you need to go for it to deprotonate, the strength that you need to do at pH 7, it's much easier than it is at pH 6, and it's incredibly more easy than it is at pH 4. So this means that the compound at a normal cell can enter a normal cell quite easy, assuming, and then when the outside is acidified, the compound might have a problem going inside the cell. And then if it goes inside the lysosome, it gets trapped because it doesn't deprotonate to come back to the cytosol, you see?
Yeah.
So just looking at simple like pKa curves, we start to see the dimension of the problem. Maybe these Lewis bases are not such a great tool to modify these rocks, these hydrophobic rocks, and make them water soluble, because patients need to take this. And what this seems, the moment we saw this, we start thinking, but are these compounds do they have better membrane permeability in normal cells than in tumor cells? If this is true, this can explain why people are taking such a high dosage, right? So what we did, because we wanted to calculate the membrane permeabilities, we wanted to have a number to see another dimension. Is it a double? Is it triple? You see how much more, how much lower is the membrane permeability at acidic pH? And for that, we had to force the compound to go where it didn't like to go, which is the center of the membrane. And we have to use simple things like umbrella sampling and coupling umbrella sampling with constant pH, which was something really cool to do. And when we did this, we could calculate the energy profiles of sunitinib while it goes from water to the phosphate region and then cross to the center of membrane, which is here. And all of this process is coupled with protonation change in sunitinib. And we could calculate the membrane permeability using the ISDM method. And this is really scary, because when we did the calculation, it's like almost a factor of 10. So what this suggests is at pH 7, the compounds really can cross membranes rather easily. So this this value, it's like almost, it's a factor of 8 or 10 to this one. And maybe not 8, but maybe like it's between 6 and 10. I don't know the exact number, but it's a huge factor. And you see, it's just a small difference in pH, and it's enough to create a huge problem. And of course, if they go into lysosomes, they get trapped there. And lysosomal entrapment is one of the mechanisms for drug resistance. So tumors, they resist drugs, especially after you do a treatment. And then if you try to do a second treatment with the same compounds, what tumors do is they overexpress membrane channels, exporters. That is known, right? They overexpress this. And what they also do is they overexpress a few pathways that lead to the genesis of lysosomes. So some tumor cells, they have up to 6 times more lysosomes than normal. So they have like it's the trash can. So it's the bin where you put the trash inside the cell. So they just produce more trash cans for the treatment. That's why the treatment, most of the time, they fail after the second or third attempt. And this is like a picture of what is going on. So the drug does not concentrate in the tumor cells. You don't have so much drug in the cytosol, inside the cell where it needs to act. And that is the main problem. It gets trapped on the outside. This is the first mechanism, which is actually the acidification of the outside is the first before exporters, before producing more lysosomes. This is the first mechanism. And of course, there's the exporters are also important.
Yeah.
And because we wanted to kind of understand, but why is it the reason why we need this Lewis base, this cationic group. And we just picked up sunitinib, and we look at one of its receptors, and you see this is electrostatic potential of the outside. It's actually neutral to positive. So there was no advantage in having a Lewis base there. I have serious doubts that when bound, this group will be protonated. It might be protonated still because there's a lot of water, it's fully solvated. But you see, the key part of the molecule is that one over here. So this is the part that actually mimics ATP and ADP, right? So this is where it inhibits this VEGF receptor. And when we look at here, we started thinking, okay, what if, right? If instead of using, people in the 60s start to introduce Lewis bases to get solubility. What if instead of Lewis bases using a Lewis acid? Maybe a carboxylic acid is not a great idea, but as a proof of concept, shouldn't it be better? Because if you think about the pKa curves of the amines, the acid should have the pKa curves exactly the opposite, just like in the flip peptide that I showed you in the introduction. So what happens? The first thing that we wanted to do is, will the compound still bind to the receptor? We did constant PHMD, and we just found out that, yeah, so the outside, the part of the compound that is outside, what it does, it simply interacts with different stabilizing groups. And most of the time it's just solvated with water. So there is no disadvantage of having an acid there. And we actually did docking for that, just to make sure that the difference in energy was not like huge difference. In some cases, you kind of have a better acid than the reason is because some pockets are very positive, others are very negative. For instance, for gefitinib, this doesn't work so well because the pocket is slightly the way it binds, it's in the region where it's slightly negative. So when you put an acid, it doesn't like it at all. Then it tries to rearrange it. But the idea is, as a proof of concept, it makes a lot of sense. And this is where we are. This is what we've been doing in these last few days, or not days, but in these last few months. And this is what we are now trying to find out. Will these compounds actually have these pKa curves that are curved, that are on the right position? Will the compound still deprotonate, or in this case, protonate the acidic and permeate membrane? And this is probably the work plan of several of these students that are here. I have a bunch of PhD students working on this project, and here comes the acknowledgement. So I would like to thank all the people who did the work. Most of the work was actually done by Nuno and Pedro Suzanne, who had in their work, PhD work plan, the idea of studying these compounds, these drugs. And of course, the funding. And I thank you all for listening to me for this at least 35 minutes with my water break. Thank you.
Thank you very much, Miguel, for a very nice seminar. So I guess everybody is convinced that the effect of pH is real, and if you want to really get correct results, you have to take that into account. So I like the periodic table next to your picture, where you took the picture with the group.
It's in the floor of my department on the outside.
Oh, I see. Chemistry. Makes sense. So I can start actually with some questions. Some of the drugs that you showed, this gefitinib and things like that, these were kinase inhibitors, if I remember correctly. But you think they also bind the VEGFR, the growth factor receptors? Is that true? Did I?
Yeah.
See?
So the initial study, we just picked up random Lewis bases. The idea was to pick up whatever drug you have, and we actually used also some antipsychotic drugs because they need to cross blood-brain barrier. They have exact same problem, and most people in medicinal chemistry, they just use the same strategy on those drugs because people have been using them successfully for 30 to 40 years. And at some point, this last table that I showed you, they are just tyrosine kinase inhibitors, because at some point we had just so many, we had to focus on just one specific case. And then, and some of these inhibitors, they inhibit more than one of these receptors. So they bind into this to the pocket of several of these catalytic domains of decay of tyrosine kinases. And whenever we had an X-ray structure, we went for the main target of the compound, but we also went for all these X-ray structures that were available, that for which we could compare, because not only we wanted to see if we modified the cationic drug for an anionic had an impact on the energetics, but we also wanted to make sure that the inside of the pocket was the same. So we wanted to have reference. We want to know where it binds to. So we were limited to those constraints. And yeah, so I'm not completely sure that all of the targets are the main targets of those compounds.
I see. It does. Yeah. I have a couple of other questions, but actually, in case somebody else has a question, I let them go first.
Yeah, I have two quick questions. One, how does PyPK work in systems with metals? Does it able to take that into account?
Yeah, but it's not straightforward. So every time you have a cofactor, you have to parameterize it. At the moment, the version that is available is only for Gromos, 5047. So you'd have to stick it into the automated topology builder from Gromos, which is developed by Alan Mark in Australia. You just stick it there and you get the ITP, and then you need to add to the databases. It's not straight out of the box, no. The only thing that is straight out of the box is really proteins. Even with lipids, if you just stick a protein embedded in the membrane, although my method allows for Poisson-Boltzmann to be calculated with explicit lipids there, all of my PK calculations are done with the membrane there present. Although we have that in that specific method, because it's a simplified version, it will strip out all the lipids and everything else, it just leaves the residues that are available in the database. If the database doesn't recognize it, just clean it. Just like PDB to PKR.
Okay, cool. Thank you. My other question is, from that first drug you showed binding, I think it was to acetylcholinesterase. Are you in systems like that? Are you able to see that proton then pop up somewhere else, like on the protein, for example? I know that like you wouldn't obviously see it happening, but
yeah. So a couple of things. Because we do Monte Carlo, what we are modeling is the jump of the proton to a buffer. So the proton does not need to have an acceptor. It's not very realistic. We know that because if the proton needs to go somewhere, and usually it doesn't go that far. So it needs to have something to accept this proton. But in our model, because we have like a buffer, it's just like a temperature bath, right? Where you can exchange energy and do whatever you like. Here you have a buffer of protons. But that does not mean that we don't study the possibility for exchange of protons, double jumps. We do that in the Monte Carlo, just exactly because sometimes the system becomes trapped, and the only way for this guy to jump into another protonation state is if this guy jumps to another protonation state. So they need to do something like this, like a spin thing.
Yeah.
And that's why double moves are very important in Monte Carlo. We need to do that. But that's a great question.
Actually, that brings me to my question. I was going to ask you, so it seems that you have been able to do a lot of drugs. So you don't have to have a standard chemical groups to tag for protonation, deprotonation necessarily. You can go with any group, and you can specify that group should be one of the groups that can be protonated, deprotonated, somehow tagged in your model.
Yeah. As long as you parameterize the groups. So you need to.
I see.
Yeah, you need to. If you are going to constant pH, you need to add those two protonation states. So this drug, you need to have it in protonated, deprotonated form.
I see. For the classical simulation, you have to parameterize the protein.
Yeah, exactly. And we have to do that. And the parameterization also allows another thing, is that we can stick the drug into water run the constant pH molecular dynamic simulation, get a pKa shift, and then adjust the model compound pKa, which is our like intrinsic pKa, so that if we had done that simulation in water with the model compound corrected, we get the experimental pKa. So we can use the experimental pKa of the compound in water to calibrate.
I see.
You see, we do that for all compounds.
I see.
That's why when we have the pKa converging to the experimental in water, it makes sense we use it as a calibration.
I see.
Yeah.
You know, the other question I had, what is the overhead of the method? Like, I mean, how much more simulations or calculations we have to do?
It's 2 to 1 for proteins, because it takes twice as long. For when you have proteins, because you imagine all the side chains of the protein that are titrating also. So when we show you, for instance, the binding as an example that Matt was asking about the donepezil interacting with acetylcholinesterase, there's tens and tens, I think even almost 100 of sites that are titrating on acetylcholinesterase side. And we don't know which one are important. Of course, we could circumscribe and say, okay, only until 30 angstroms. All the rest, just keep them quiet. But still, it's a large overhead, because it can go to 10, 20% to even 60, 70% when we have a lot of sites titrating. Because this is Poisson-Boltzmann. It takes
I mean, 2 to 1 is wonderful, actually. I was expecting something like, I don't know, 100 to 1 or something like that. So this is really impressive.
But imagine, sunitinib interacting with the membrane, it's maybe 5% overhead, maybe 10 worst case scenario, because it's just one group titrating. The lipids, we just keep the lipids quiet, because we use this phosphatidylcholine, which only protonates around pH 2.5, right? So
I see. Hocha, you had something?
Yeah, I think the first is this constant pH is different from the one we have in NAMD, right? So this is probably based on lambda dynamics. So you can have multiple many possible protonation site calculated. Calculated at once. So that would be much less overhead. Just I have something that I think right now I'm sort of there are some subjects I want to investigate through constant pH, but I think I'm sort of getting a headache because I think maybe just have you comment on this. There are a few molecules of interest with constant pH, but we don't know how to handle. One is like phosphorylserine, phosphotyrosine. Yeah, basically phosphorylated protein residues. The other is cardiolipin.
So you are hitting all the subjects that I already studied. That's cool. So for the phosphorylated residues, I have the parameters for gromos. I don't think I have a student working on it. I don't think we ever extended this to amber and charm, but for gromos we have it sorted because it's tricky, because there's a lot of combinations. That's why our method uses a lot of tautomeric forms. We use tautomers for carboxylic acids. We allow the proton to go into the 4 positions of the carboxylic acid. So it's the 2 front positions because you have 2 oxygens and the 2 back positions. So when you have a phosphate,
so is that all the tautomer is built into the same topology in that lambda dynamics?
There are like virtual sites. They are always there. They are allowed to exist and to disappear. Yeah,
I see.
And this is very straightforward for gromos and for charm. We are now finalizing for amber. For amber, you actually need some tweaks there because of some of these hydrogens have Lennard-Jones, and we need some tricks. We are doing that with Adrian Reutberg. So Adrian's method is the closest that there is to the Antonio Batista's method. We are all quite good friends because we end up developing parallel methods. The method is almost the same with Adrian. But the idea of having this tautomeric solves the problem that you're raising. So when you have a phosphate, you have something like 7 states that are possible.
Yeah, it's
okay.
all,
3 of them
we
are
can
the
do
double
rotation
protonated, and
yeah.
only at very low pH they are relevant.
Right.
But the other 3 neutral are really cool because it captures the deprotonation that happens at pH 6.5. This is incredibly important for people that are interested in changing the charges, because -1 and -2, which is what's happening with the phosphate, can have a large impact. That's why, well, that's why all these regulatory lipids have these phosphates dangling around, is because of it changes completely the electrostatics, and the pKa's fall on top of pH 7. So at pH 7, there's like, it's a lighthouse. So all of these like phosphatidylinositol and phosphatidic acid. Usually the ones that they are called the signaling lipids are usually the ones that have exposed phosphates. And because we knew that, we tried that. The first time I did a model to titrate a lipid was cardiolipin. Why? Because what is his name? He just died this December. Haynes, Tom Haynes. So Tom Haynes in protein electrostatics. Tom Haynes is a guy coming from biology into the lipids, biophysics. And he was always saying cardiolipins, the skating protons theory, where protons are just jumping and the proton gets trapped inside between the 2 phosphates of cardiolipin. This is his theory that he dared me to go and check it. And the problem is exactly what we were discussing, Emma, in the beginning of this. When you have such a strong interaction, it's so strong, it happens with cardiolipin, it's such a strong that differences in force field, if you change a little bit of the parameterization of these phosphates and the lack of polarizability, charge transfer, which I think are phenomena that will happen with cardiolipin, the moment you do that, you cannot stabilize it. It becomes unstable. And that's why I don't believe in any simulation, unless you use coarse grain. All the others atomistic simulation of cardiolipins are probably wrong because they are not capturing what the stability of the electrostatics. But I would claim that mixtures that have more than 10% of phosphatidylserine are probably wrong. But for instance, Charm nowadays, you see so many papers coming out of Charmgy, and they give you and they allow you to do all of these simulations with phosphatidylserine.
We do 50% PS all the time, actually.
Yeah, and I already had this discussion with the pastor.
Is that related to the pK of the head group of serine? That I see.
Yeah, the carboxylic acid, the pKa after 10-15%, the pKa goes as high, and then a certain amount of this phosphatidylserine starts to become protonated.
Right.
And what force fields do is that they have the experimental data to fit. They just change the parameters somewhere else to compensate for that.
Yeah, exactly.
Yeah. But it becomes very problematic because then you have charged surfaces.
We look away from this really fundamental problem because we don't know how to handle sort of long simulations with treatments like what you do. So it would be nice to have something similar in NAMD, Dave, right? What do you think? Yeah.
I didn't get it. Would be nice to have something similar
something in NAMD for using your methodology because it's pretty fast. What we are doing, because again, just checking one site at a time, let alone hundreds of sites, takes forever. You have to try, it doesn't work, it fails. Tautomeric states. There are so many different ways.
Yeah.
You can protonate one site, like you said, for the phosphate. And then there are so many sites, and you have to try them all. So that's why it takes a really long time to kind of do other types.
There is a downside, which is most people don't like the idea of using Boltzmann because it's slow and because we are kind of outsourcing the pKa calculations to Boltzmann Carlo, right?
Right.
So
I was about to ask that actually,
sure.
But maybe this is an ignorant question. Why Poisson-Boltzmann? I mean, it's a very detailed description of the electrostatics, but do you need something that detailed to do what you're doing?
For some problems, I don't. Yeah, I could get away with very simple, very rude calculations for sure. Yeah, but then I don't know which ones. A priori, I don't know. Only after like long years, I know that I can get away with simpler ones. And then instead of going into some of those simpler methods, do you know what I decided to do? So I decided to calculate all pKa values of the complete PDB data bank, and now also a huge part of AlphaFold database. So I have the database and I'm training AI to actually do it. Because it's very strange, but why are you feeding computer data to AI? Because I think it will be the future, because it's very slow. And if AI can give me a protonation or the energies, I only need the energies because I can still use Monte Carlo. I don't care.
Right.
But if I can do that, then it cannot get as cheap as that. You see, even if I go to other methodology, there are other methods alternative to Poisson-Boltzmann or other PB solvers that are almost very fast. They're incredibly fast compared to Delphi and the classics, right? But why do it when you have all of that problem? When if you can train an AI that, and we did that, it gives you instantly the energies. So the pKa, we did first with the pKas. The pKas are no good for us. We really need the energy so that you can go to Monte Carlo. And if we have that, and answering to your question, Eman, if we have that, imagine we have an AI that can look at the conformation of the protein and gives you protonation energies. And you go to Monte Carlo, which is, it can be expensive, but it depends on how exhaustive do you want the Monte Carlo to be. But you can get it quite cheap. So you can join them together. Why not couple that to any MD package? You can couple that with an MD package.
Absolutely. No, I have no doubt it's going to improve the outcome and the results that we get from MD. Absolutely.
Then it will be an overhead of what? It's less than 5% because you still need to relax the solvent, but it's like, that's 2% or 3%.
Yeah, absolutely. Any other questions, guys? I know it's pretty late, 10 p.m. now, your time, so we don't want to
no problem.
for too long, so I don't see. Eric.
I had a question. Thanks for the talk. So I was wondering, you reported some numbers for the permeability of sunitinib, and so you're saying like that low pH like drastically reduced the permeability that you calculated. Where does that resistance to permeation come from? Is it at the interface region where the protonation deprotonation needs to occur?
It's an incredibly good question. There's two barriers. There's the barrier of coming to water to the membrane, and then there's a barrier of the tails. And it depending on how polar, apolar, this is what we learned recently. Depending on how polar your compound is, one of the barriers will prevail. And of course, if it's a compound that is in between, then both barriers are relevant. But for instance, for these hydrophobic compounds, the barrier is most likely at the tails. But it's not only being hydrophobic, it's the fact that they have this size. This size of compounds, the main barrier will always be crossing from one minimum that is below the phosphate level to the other minimum on the other side. So there's always a barrier. That's why in MD, we see them going from adsorbed to inserted, but never crossing to the other side because the barrier there is higher. But there's a barrier that also counts. So we could, the idea is some people are doing is they are using this information from different kind of compounds, chemical groups, so that they can kind of predict automatically without doing all those heavy calculations to predict what will be the permeability. But these are very rough, right? So we are using this the ESTM, so ISTM method, it's a rough approximation. And these values are like 3 or 4 order of magnitudes higher than experimental measured membrane permeabilities. The reason is several-fold. One is the method itself has limitations. So I only believe in differences. The absolute value is almost meaningless. The reason is we are using very fluid membranes. The moment we see, if I add cholesterol to the membrane, membrane permeability will decrease probably 1 order of magnitude. But in my setup, if I do that, I see distortion of lipids. I see a lot of bad things because I'm trying to force something that is much more difficult to happen. That's why we move our model to this the sweet spot. We go to the sweet spot and we make things happen where we can measure differences. But it should be kind of interpreted with the grain of salt. And the punchline is, we did it because we kind of knew the result, right? I did the whole interpretation for you while I was presenting the pKa curves and the difference. If you need to go so deep so that it can deprotonate and you can see the abundances from constant pH MD, you see that the compound doesn't like to be inside the moment it gets ionized. So if you force it to be more ionized, it's simple kinetics. It's not kinetics and thermodynamics, it's both, but kinetics will also kill you from the beginning. So you don't need to have such a difference in the PMF because kinetics will also give you a punch.
All right. Okay. So we let the guests go and back to his life. So thank you very much again, Miguel, for the nice
Really, it was a pleasure, huh?
and answering so many questions. And good night. Thank
Yeah.
you, everyone.
If you
Bye.
ever come and visit Lisbon, please come
Thank you, sir.
and visit. There's not many universities.
I like the animations on your website, by the way. Very cool.
Yeah. Your website is as good as the best graphic designer in your PhD students.
Yeah, of course. Exactly.
I was blessed with one guy that really loves it.
Okay, thanks again, Miguel.
Okay, see you then.
Bye-bye.
Have a nice one.
Bye.